Keeper 2.3, the intermediate value theorem, and continuity. All right, so the definition of continuity basically states that in order for a function to be continuous, the function must be defined at the point. The limit from the left must equal the limit from the right of that point and must equal whatever the value of that point is. So again, the limit from the left has to equal the limit from the right, which also has to equal that point value itself. The definition that I just read sounds a little confusing, but basically what I'm saying is that if you were to take a graph and run your pencil along the graph, if you can run your pencil along it without ever picking up your pencil, then it's continuous. If you had to pick your pencil or pick up your finger at any given point, whether there's a hole or a jump or anything like that in the graph, then it's not continuous at the point that you picked up your finger. We can also look at functions that are right continuous and left continuous. Right continuous functions basically are functions that are continuous on the right. So as I travel the function on the right, I don't have to pick up my finger, and it's defined at the point on the right. Versus a left continuous function would be I would travel along the graph on the left, and if I never pick up my pencil traveling along that graph, and it's defined at the point on the left, then we say it's left continuous. And we'll see a couple of examples of those in a little bit. All right, so we have three main types of discontinuity. Our first type of discontinuity is removable. That's a hole. So that could be like any type of graph that has a hole in it. Generally, you see that type of thing when you're looking at a rational function. So like if I took a function like something like this, maybe something like this, and then I have a hole, and then it keeps going, something like that. That would be a removable discontinuity. We did one earlier that was like, or in a previous lesson, we did one in the graph of something like this, and there was a hole right here, but then it was defined up here. That's a removable discontinuity. A jump discontinuity would be like a piecewise function. So for jump, I would have something that looks like maybe something like this, closed circle, and then open circle, something like that. That would be a jump discontinuity. Then our infinite discontinuities, that's when you have an asymptote, like a vertical asymptote in your graph. So it would be something like, I don't know, you have a curve going like this, then you have an asymptote coming here, and then a curve going like that. That would be some sort of infinite discontinuity. All right, so here's our first example. And again, you want to print off this picture and include this picture in your graph so that you have it to refer to when you look back at your examples. All right, so the very first question says, does f of 5 exist? Remember, that has nothing to do with limits, has no limit sign on there. They're simply just asking if the function exists at 5. So what I would do is I would just go over to my graph at 5, and I would determine whether or not I had a point there. If I have a point, then it exists, and if I don't, then it doesn't. So going over to my graph, f of 5, even though I have a hole down here, I also have a point right here. So f of 5 exists. Not only does it exist, it equals 0. All right, the next question says, does the limit as x approaches 5 of f of x exist? Now remember what your definition of the limit says, that it has to exist from both the left and the right-hand side of 5. So again, I don't care what it is at 5, I care what it is on the left and the right. So on the left-hand side of 5, my graph is going to y equals -2. And on the right-hand side of 5, my graph is also going towards -2. Therefore, the limit does exist, and the limit actually equals -2. All right, part 3 says, is f of x continuous at x equals 5? Well, given the definition that we just had, remember the definition says, in order for it to be continuous, it has to be defined at 5, which it is. The limit from the left has to equal the limit from the right, has to equal the limit itself, which we just figured out in number 2. So it does exist, and the limit exists. But is it continuous? I'd have to say no. And the reason why it's not continuous is by definition, the limit from the left must equal the limit from the right, must equal the limit, but it also has to equal the function at that point. In other words, this 0 that we found in part 1 must equal this -2 that we found in part 2. If they don't equal, then that means it's discontinuous, which actually makes sense when you look at the graph, because when you look at the graph, if I take my highlighter and I draw along the graph at -5, I have to pick up my pencil to account for the hole. Therefore, it's not continuous. All right, question 4 says, what new value should be assigned to f of 5 to remove the discontinuity? In other words, what should I do to fix my hole? What can I do to fill that hole up? Basically, they're asking you, how can I move this closed circle up here? How can I move this back to the graph so I no longer have a hole there? Well, that's quite simply all I have to do. Instead of letting f of 5 be 0, if I let f of 5 be -2, this point will come down here and close it up. So what should I do to assign? Or what value should I assign to my function? Well, I should let f of 5 equal -2. That would fill my hole. All right, next question, number 5. Does f of 2 exist? So again, I'm going to go to my graph. I'm going to go to 2, and I want to see if I have a closed circle. I don't want asymptote or anything. I want to make sure it's closed up and clean there. Well, looking at my graph at 2, even though I have an open circle up here, I also have a closed circle down here. So f of 2 does exist at the closed circle, and f of 2 equals -2. That's the y value that corresponds to f of 2. The next question says, does the limit exist at x equals 2? Well, the limit from the left at 2, so on the left-hand side, is going up to 3. And then the limit on the right of 2 is going down to -2. So does the limit exist? No, it does not, because the limit from the left equals 3. The limit from the right equals 2, or -2. These two numbers do not exist, and therefore the limit from the left doesn't equal the limit from the right. The limit doesn't exist. I can ask you a further question, even though it's not on the slide. Well, is it continuous? Well, clearly it's not continuous because, again, the limit from the right and the left have to equal in order for it to be continuous. Again, I could use my pencil trick to determine if it's continuous. All I have to do is say, take my pencil or my highlighter, draw from the left. Oh, I had to pick up my pencil to continue the graph on the right. Therefore, it's not continuous. All right, question 7. Does f of -5 exist? So what I'm going to do is I'm going to find -5, which is right here. And I want to make sure that I see a closed circle. There's no holes or gaps or anything. So I definitely see at -5, I see an open circle. And I don't see anywhere else on this x equals -5 line that's closed up. Therefore, this function does not exist at -5 because I have a removable discontinuity. I have a hole at x equals -5. All right, so does the limit exist at -5? Well, we have to check the left and the right. So going on the left side is approaching 2. And then the right side of -5 is also approaching 2. Therefore, the limit exists because both sides are approaching 2. Number 9 says, is f of x continuous at x equals -5? Again, remember our definition. The limit must exist from the left and the right, and it has to actually, like the function itself has to exist at that point. In other words, the question in number 7 must equal the question in number 8. Well, the question in number 7, our function doesn't even exist there. So even though number 8 is 2, this does not exist in number 7. Therefore, the limit, therefore it can't be continuous because the limit doesn't equal the function value because the function value doesn't exist. All right, question 10, it says, what new value should be assigned to f of -5 to make it continuous at x equals -5? And again, what they're really asking here is, how can I close my hole? What value should I plug in at -5 to close my hole? Well, the hole happens at y equals 2, so the value I should use to close my hole is going to be 2. In other words, to remove the discontinuity, f of 5 should be 2. Question 11. Is f of x right continuous, left continuous, or neither at x equals 2? All right, so x equals 2. So I'm coming over to x equals 2. I notice that I have on the left-hand side, so this piece of it, I'm going towards a hole. On the right-hand side, I'm going towards a closed circle. So when they ask you is it left continuous or right continuous, you want to pick the one that has the closed circle. And the reason for that is because it has to be defined at that point as well. So on the left-hand side, when I'm traveling, I have to pick up my pencil for the open circle, so that's not going to be continuous. But on the right-hand side, I'm traveling and my pencil stays closed, or like I never had to pick it up because the hole stays closed. That means this thing is right continuous at x equals 2. All right, is it right continuous, left continuous, or neither at x equals 7? Well, at x equals 7, I can use the same type of thought process. On the right-hand side of 7, I have a piece with a closed circle. On the right-hand side of 7, I have a piece with an open circle. So the part that's going to be continuous is the part with the closed circle. That means it's continuous is on the left-hand side. So for the second part of the question, it says, well, my answer is x is left continuous because the limit equals -2 and the function value is also -2 on that left-hand side. All right, the very last question of this type, it says list all places where f of x is discontinuous and state the type of discontinuity. So all of the places that is discontinuous, remember we have three basic types of discontinuities. We have holes or removable, we have jump, and we have infinite. So I'm looking at my graph and I'm trying to list all the places where I possibly have a hole, an asymptote, or a jump in the graph. So looking from left to right, the very first one that I see is right here at -5. And we already discussed this on a previous slide, and we saw that at -5, because there was a hole in our graph, we had a removable discontinuity at -5. The next type of discontinuity I see is right here at -3. There's a clear asymptote in this graph, and because I have that vertical asymptote at x equals -3, I would say I have an infinite discontinuity. At x equals 2, so right on this line that I already drew. On the left-hand side, I'm up here at 3. On the right-hand side, I'm down here at -2. We call that a jump because the graph literally jumps places. It was going one way and then it jumped and started doing something else. So at x equals 2, we have jump discontinuity. Then I have an issue here at 5. So at 5, again, I have an open circle and then I have a closed circle above it. Again, that is what we call removable discontinuity because there's a hole in the graph and we could fill that hole. We could remove the discontinuity if we wanted to by filling the hole. And then the very last one we have is at x equals 7. And again, I'm down here on the left-hand side, I'm down at -2. And on the right-hand side, I'm up at 2. So our graph literally jumped places. And so we call that jump discontinuity. All right, the next thing that we want to go over is very quickly, we want to talk about discontinuities from functions. Like if I give you the function, what type of discontinuity would you have? Now this very first function, and again, you have to have some kind of idea of what these functions look like or what they're doing. So in this very first one, number 13, I noticed that I have a rational function. And if I was to imagine what this graph looks like, if I was to kind of get a visual in my head of what this graph looks like, I know it's going to be a graph with some sort of vertical asymptote as well as a horizontal asymptote with 2 little wings or possibly 3 wings or 4 wings. But I know it looks like rational. So like a quick sketch, and again, you don't have to sketch it. I'm just trying to make sure you guys see what I'm talking about. But a quick sketch of this would be something like at 3, I would have like an asymptote, and then I also have an asymptote at 0, and my graph kind of looks something like that. All right. So again, you didn't have to sketch that out at all, The idea is that you should be able to look at this and know what it looks like and know that you have an asymptote at 3. Now, why do we have an asymptote at 3? We have an asymptote at 3 because our denominator cannot equal 0. So x minus 3 cannot equal 0. Well, if x minus 3 cannot equal 0, then that means x cannot equal 3. All right, and because x can't equal 3, and that's in your denominator, you know that you have an asymptote, a vertical asymptote in your denominator. Well, if there's a vertical asymptote in our problem, we know the type of discontinuity had to be infinite discontinuity. The next question, I see a piecewise function. Anytime I see a piecewise function, I kind of get the feeling that I probably have a jump discontinuity. So I probably have one piece of the graph and then it like jumps off to another piece. But I definitely have to check it because sometimes with piecewise functions, they don't actually jump. Sometimes they connect. So even though I see a piecewise and I feel in my heart that it's possibly a jump discontinuity, I want to check just to be sure. So what I'm going to do is I'm going to plug in the value of the limits for the piecewise function itself. So for the first part, I'm going to plug in 1 into the first equation. And I get 3 times 1 minus 1, which is 2. And then I'm going to plug in 1 to the second part of the equation. And 4 times 1 minus 2 is also 2. This tells me that even though it's a piecewise function and the graphs on each side look a little different, at 1 itself, they equal the same thing. So I will not have a jump. I will not have any type of gap in my graph. That means that this function is continuous. All right, the next one, again, I see piecewise. In my heart and my soul, I feel like that has to be a jump in this graph. But again, they could possibly connect, so I need to check. So again, I'm going to take whatever is over here on my piecewise function and I'm going to plug it in. So I'm going to get 2 times 2 minus 5, and that is 4 minus 5, which is negative 1. And then I'm going to plug it into the second equation, so 3 times 2, which is 6. These two things are not the same. Negative 1 and 6 are not the same. That tells me that there had to be a jump in my graph, so I have jump discontinuity. The next one looks a little weird. Again, it's a rational. Usually with rationals, I'm thinking there's some sort of asymptote, like an infinite discontinuity, but I have to check to make sure that I do not have any types of holes in my graph. So I got to check that. All right, so what I'm going to do is, like we do with most rationals, I'm going to try to factor it. So on the top, I'm going to factor out a 2, and I get 3x minus 1. And then on the bottom, I'm going to factor out a 3, and I get 3x minus 1. Now, if you remember back in your Algebra 2 days, when you have the same factor on the top and the bottom of a rational function, that is actually a hole in your graph. So this becomes a hole. All right, and not only is it just in your hole, specifically a hole at x equals 1/3. All right, because that's what the value would be if I set that piece in parentheses, the piece that I canceled out, if I set that equal to 0. So what this tells me is that I have a hole in my graph because all the factors are taken away out of my denominator. I do not have any asymptotes. So the type of discontinuity I have is a removable discontinuity. All right, the very last one, again, I have a rational in my heart. I think that it's going to be probably an infinite, possibly removable if I have factors that are the same, but I have to factor it to be sure. So we'll factor this out. The top, I'm going to take out a 2. And then on the bottom, I'm going to take out an x. Right away, I notice I have 2 factors alike, so that's definitely a hole. But I still have an x down here, which would give me an asymptote. So not only do I have a removable discontinuity, I also have an infinite discontinuity as well. All right, so now that we figured out how to figure out discontinuities, I want to see if we could also figure out how to find values that will lead us to be continuous. Like, I don't want this constant, I want to be continuous. So what value in this problem of a would make this function continuous? Well, thinking logically, at 2, since 2 is our breaking point of the piecewise function, at 2, I want the top and the bottom to be the same because I don't want to jump. If I have a jump, then I have a jump discontinuity. So basically what I'm saying is when I plug in 2 into the function, I want to make sure that I'm getting the same number out when I plug it into the top and when I plug it into the bottom. So when I plug in 2 into the top, I get 2 times 2 plus 3. That's 4 plus 3, which is 7. All right, then I can plug it in the bottom, and I get a times 2 plus 1. All right, now remember that a plus 2, or a times 2 plus 1, I want to equal 7 because the top equals 7, and I want it to equal the same thing. So now solving this, I get 2a equals 6, or a equals 3. All right, so in order for this thing to be continuous, a would have to equal 3. And of course, I can go take that 3, plug it back into my function and check my work to make sure that it actually works out. Now, the catch to this is when you write these continuity statements, you have to say why. Why does it work? You can't just say a equals 3 and call it a day. We didn't actually do any calculus. So in order to get full points for this question, you have to state why it works. So I would say something like the value that makes this function continuous is a equals 3. And that's because the limit on the left equal the limit from the right equal the limit itself, which equal the value at 2. That's not a suggested phrasing. That's a must phrasing. If you don't put it, you will lose half points on this question. You have to write what I call, this is what I call the limit statement. All right, and again, you must include that on every single problem that you do where you're trying to prove that something or show that something is continuous. All right, so next we have something called the intermediate value theorem. The intermediate value theorem is one of those big, important concepts that they like to test on the AP exam. All right, so the intermediate value theorem, the definition seems a little confusing when you read it, but if we talk it out and write down what they're saying, I think it becomes a little bit easier to understand. So let's start. If a function f is continuous, so if the function has no holes, no jumps, no infinite discontinuities, so this function is continuous and it's continuous on some interval from a to b. So let's start with that. So we have a and we have b. And it's continuous in that region. That's not to say that it's not continuous outside of that region. It could be discontinuous at z or k or something like that, but between a and b we know it's continuous. All right, so then we have n, some number n, between f of a and f of b. So if this is a, let's just make a point there, and let's call this b, let's make a point there. This value right here is f of a. And this value up here would be f of b. Those are the y values for a and b. So they're saying that there has to be some number n between f of a and f of b. All right, now again, if this thing is continuous, this graph can look as crazy as I want it to look, but either way, I know from a to b, I never had to pick up my pencil. I have a smooth curve. All right, so I know that there's some number n, right? There's some number n that's between f of a and f of b, such that when I look at my graph, so if I go across and bring it down, there must have been some c that equaled that number n. In other words, if I'm a continuous function between 2 points, then I can find points in between those 2 points. Again, it's kind of a theorem. It's just a lot of people see it as almost a common sense theorem. They don't see what the big deal is because it almost just, it's like one of those situations where you just say duh. But the wording of it and the way it's worded sometimes makes it a little bit difficult to understand. All right, let's look at an example of the intermediate value theorem. This example is asking us to verify the conditions of the intermediate value theorem and find the value c over the interval 2, 6, such that, or for the function f of x equals x squared plus 2x minus 11 when f of c equals 4. So in order to do this, the very first thing we need to confirm is this function continuous? Well, in our case, we have a quadratic function, an x squared function, which we know is continuous over its entire domain. So if it's continuous over its entire domain, it's for sure continuous over 2, 6. That's the first thing I'm going to say. F of x, or since f of x is continuous from 2 to 6, right? I'm kind of like telling the story. So since I know this, since I know it's continuous, and I also can figure out what the values are at those endpoints. So at 2 and 6, I can figure out what those y values are, or those f of a, f of b values. So since it's continuous, and f of 2, calculated out by plugging it into the formula, equals -3, and f of 6 equals 37. So since I know that it's continuous, since I know f of 2 equals -3 and f of 6 equals 37, I also know that 4 falls between -3 and 37. I should be able to find some value c that gives me 4. All right, so that sounds kind of crazy. It sounds a little weird. Let me draw it out. Maybe that will help you guys visualize it a little bit better. So if I draw this thing out, basically I'm just going to draw literally the definition of the intermediate value theorem. So my A in this example is 2. And then my B would be 6. I also found out that my f of A was -3. And my f of B, or f of 6, was somewhere up here at 37. So, like that. And I know the function is continuous. So I'm just going to curve it out. Since it's nothing real funky, it's just a quadratic. I know it's continuous, and I know I have those boundary points. I also know that 4 is between -3 and 37. So that means I should be able to find some y value of 4 in the graph. So like if I was to go across and then go down, I should find a y value. And not only should I find a y value of 4, I should be able to find the c that corresponds to that y value. In other words, again, since it's continuous, since I know f of 2, since I know f of 6, and the problem that they're asking for, the 4 that they're asking for, falls between f of 2 and f of 6, I can basically figure out my final answer. So I would say therefore, so 3 dots means therefore, there exists, that's the backwards E, a C in, or an element of, that's the forward C, 2, 6, such that f of c equals 4. All right, so I know I just gave you a lot of symbol, a lot of notations. Those notations are acceptable on the AP exam. So let me give you a little key of the symbols. So again, the 3 dots means therefore, the backwards E means there exists, the forward E means like an element of or in, and then ST means such that. All right, so because I know all this stuff, I know I can find the C such that f of c equals 4. All right, so once I have all that, basically all I'm going to do is calculate it. And so I can do f of c equals c squared plus 2 times c minus 11. And I know that has to equal 4. And then just using algebra rules or algebra tricks, I can say c squared plus 2c, subtracting the 4, so minus 15 equals 0. Then I would go about factoring this. So it looks like 3 and 5, c plus 5 and c minus 3 equals 0. And then I know that c equals -5 and 3. Now technically those are the 2 answers, but remember we want a c between the interval that they gave us. So the whole thing we were guaranteed a c between 2 and 6. So I don't want the c equals -5 because that's not between 2 and 6. I just want c equals 3. All right, so the very last problem for today, they're asking us to use the intermediate value theorem to show that the function f of x equals x cubed plus 5 has a root in the interval -2, -1. Notice this time they didn't ask us to find the root, even though we could. They just wanted us to show that there must be a root. All right, so the very first thing, again, we want to check to make sure the function is continuous. And that's an easy task for this one because it's a cubic function. Cubic functions must be continuous over the entire domain. So again, if it's continuous on the entire domain, it's continuous from -2 to -1. So first thing I'm going to say is f of x is continuous from -2 to -1. The next thing I need to figure out is my f of a and my f of b. So my f of a would be f of -2. Plugging that into the function, I get -3. Then I want to check the other endpoint, so f of -1, plug that into the function, I get 4. Now, in order for me to have a root, we need to understand what a root is. If you remember back in algebra, a root is the same thing as a 0. A 0 is the same thing as an x-intercept. All those words can be used kind of interchangeably. We use them for different reasons, but either way, they're saying I want this thing to have x-intercept or a root or a 0 between -2 and -1. So since it's continuous, since f of -2 is -3 and f of -1 is 4, we know that we have a 0 that falls between -3 and -4. All right, because literally the number 0 is between -3 and -4. Well, since this is the case, therefore, there must exist a c in -2 to -1 such that f of c equals 0. So even though I didn't find the root, I figured out that there had to be a root because my y values went from negative to positive, which meant there had to be a 0 in between there. That's it for today. Let me know if you guys have any questions.